Question that I get in different forms on YouTube a lot of, well, why are you doing this when we have space telescopes that can take the most brilliant pictures ever, and you're never going to be able to match something like Hubble or the James Webb? And I think it comes down to the fact that we're doing amateur astrophotography. Sometimes when people hear the word amateur, they just think that means that we don't know what we're doing. But the word amateur actually comes from the Latin lover, because we love astrophotography, and that's why we do it. We're into the experience of it. We can't stop it. We can't stop just wanting to get out there in the night sky and taking pictures of it and getting our own pictures of it. Not just seeing, the best professional picture, but there's something about the pride of taking your own picture and sharing that with your friends and family that is completely different. And I first discovered that almost by accident. I was on a trip to Iceland. So in early 2014, I got my first sort of professional job as a librarian at the University of Delaware. And so I saved up my vacation week, and this is my first sort of vacation. And I wanted to see the aurora because I had seen them very briefly when I worked in Alaska, but it was at the end of the summer. So the night was still a little bit hazy, because if you're in Alaska, you're very far north, and it doesn't really get true dark until like September. So in August, when I saw them, they were cool, and I could see the movement, but I couldn't really see them as well as I could if it was really dark like the end of the winter. So I went to Iceland, and I knew that if I could see the aurora, I just wanted to spend as much time as I wanted. So I didn't go on any kind of tour group. I rented a 4x4 vehicle, which in the winter is feels dangerous in Iceland because it's all ice roads, right? You're not actually seeing the road. You're just driving on pure ice with the snow blowing across it. It's always windy. But it was a lot of fun. And the very first night driving, I saw my window something sort of moving along the horizon. And when we got out of the car and looked up, it filled the entire night sky from horizon to horizon. Just a tremendous show. And what I was really interested in photography at this time, because I've been a photographer forever, was this time-lapse photography, which is already a little bit of a specialized photography, but astrophotography brings that to like a whole new level in terms of technical stuff. I thought time-lapse photography was technical, but astro is like just beyond that. Time-lapse, all you really have to do is just set up the camera and take a sequence of photos, so one after another, just like we do in astrophotography. But with time-lapse, instead of stacking them all down into one photo, like we do with deep sky astrophotography, with time-lapse, you sequence them into a video and then play it like this. And it can show the interesting motion of things. Like you'll often see it with building construction and people working, but it's great for the aurora too, because what's so great about seeing the aurora in person is the movement. The color isn't as brilliant as this, but the movement is so mysterious and cool to see with your own eyes. And it's not as fast as this. The time-lapse, by its nature, speeds up the motion of things, because we're taking maybe a half an hour, 20 minutes of time and compressing it down to about 10 seconds. Because these are all long exposures, and there's hundreds of them, one after another. And then when you sequence them into a video to make it smooth, it compresses time down. So this was the first night. Then this was maybe like the third or fourth night. And this night was really cool. I don't know how you can see this, but here in the foreground, this is water. This is what's called a glacier lagoon. And so it's just the glacier is melting into this little pond, basically. And it was very still because it's inland. And it's sort of surrounded by these like hills and mountains. And what was so cool about this is sort of a famous spot to see aurora and photograph it. So this was my first star party. This is with, and it was a star party with people from all over the world. I met people from Japan, Germany, all these different people who were sort of aurora chasers. Like if you've heard of eclipse chasers, there's aurora chasers too, who go all over the world just hoping see and photograph the aurora. And so, of course, they had lots of tips. Some of those tips way beyond me. This is probably the first night I'd ever even heard the term astrophotography. Because when I went, I was just thinking, I'm here to view and photograph the aurora. I'm doing aurora photography. But they were telling me more about astrophotography. And I did get some tips before I left about, the exposure length and things like that. And so when I looked at this footage, I was just amazed at how many stars were in the pictures too. Not just the aurora, but all the stars. And I got a little bit obsessed right here with taking photographs of the stars, just because something about them I found so beautiful. And this time-lapse movement of them I also found really beautiful. The way that the aurora seems to be moving this way, and the way that the stars are moving in an opposite way. And it just sort of, why is that? What's going on physically to make that happen? But I was so into time-lapse that I didn't think of even taking like a single photo. But then when I got home, I realized, well, a time-lapse is just a sequence of single photos. I can take any of those out of the time-lapse and process it. And so I did, but months later. But when I did, I was shocked by how much was there in the shadows. And that's something really interesting about astrophotography, is that when you just take a JPEG picture on your camera, it can often look like nothing, or maybe just like a little something there. Sometimes it almost looks like what your eye can see, just stars. But when you go to the computer and you process it, and you just take the shadow slider or the exposure slider and you move it over, all this stuff, all these colors come out of the dark areas of the picture. And so this is real, even though our eyes can't perceive it, because our eyes aren't really rid of the night sky, because reds and pinks are especially difficult for our eyes to perceive in the night sky. Green is a little bit better because we have more photoreceptors in the green spectrum. But red is especially hard, so we didn't see any of this pink and red, but it is really there. And here's evidence this is all real too. This is the glow from an active volcano in the middle of the island. So this was sort of my first experience with astrophotography, and I always tell people I got extremely lucky because this was a great hook, right? If you just, on your first try, you get a picture like this, that's a really good hook into the hobby. And so I was really excited to do more of it. But at this point, I only thought of it as something that people do on trips to really beautiful places. And so that's all I did for like the first year, is when thinking about trips I was going to take, I was thinking, well, how can I incorporate a dark sky into this trip? And so for work, I was going to a convention in Las Vegas and looked up, well, what are some nearby dark sky places, and found that Death Valley National Park was, I think, only 4 or 5 hours drive. And Death Valley is one of the darkest places in the United States. One that people out west have now told me is darker is Big Bend National Park in southern Texas. And the other thing I'll just quickly say about dark skies is another reason people might not always mention Death Valley is it's very low elevation, and typically for the dark skies we want to find high elevation because then you're above many layers of atmosphere. So conditions can sometimes be weird at Death Valley, but it is a very dry place, so you don't have all the moisture in the air that we have here out on the East Coast. But this blew me away. It was much darker than what I saw in Iceland, in true World 1 sky. And when you're out on this area, this is called the playa, where it's very flat for just miles, you really feel you're in a bubble of stars. Like it almost feels like they're coming below the horizon at you or something. Like when you look up, if you're laying down on the ground, all you see is the night sky. You don't see even the horizons. You just see stars. So you feel like you're actually out in space almost. And I didn't really know what I was doing with Milky Way photography yet. And so it's hard to see, let's see if I can turn on my brightness at all. Probably not going to work. No. It's hard to see, but there's some stones down here, and those stones have like a trail. And at the time, they didn't really understand why these giant boulders were moving and creating a trail on the playa. They set up some video cameras and they figured out that occasionally, like maybe once a year, maybe once every 3 years, the entire playa gets a thin layer of ice, becomes a skating rink. And then even just a gentle breeze can move those boulders, and that's how they create those trails. So it's a cool science case where it's like, it was a pretty simple thing to figure out, just like set up a video camera and we figured it out, but there was a bunch of different theories before that. Anyways, what I was trying to do with this photography was get the boulders in the foreground sort of in focus, and the Milky Way sort of in focus, and have this trail leading your eye back to the Milky Way. Because I didn't know anything about what was available with computer stacking and blending and things like that, I was trying to do it all in camera. That was sort of the kind of photographer I was at the time. And so I picked a focus point sort of in between the Milky Way and the stones, and then that makes the Milky Way a little bit out of focus. Which is still, I think, a cool photo, but if I look at it today, I of course have like a lot of critiques for myself that I could have made it better. And what I would do today, taking the same photo, is I would do blending, where you can take one photo of the foreground and then one photo of the Milky Way, and in the computer in Photoshop, easily just put those two photos together. Or you can even do stacking with Milky Way and take many photos of the Milky Way to get even a more, less noise, and a stack of the foreground too. It's getting a little complicated, but the point is when you look back at your old photos, you're going to see a lot of things that you can improve, and that's another thing that I love about the hobby is you can always keep improving. When you look back at your old photos, you'll think, oh, why did I do it that way? I would do it this way today. So after this trip, I realized I loved this. I needed to do astrophotography more often than just on trips. So I started researching. At the time, I was a librarian, so I think I was looking at books more than online. And a lot of the books were actually pretty out of date at that time. And they were talking about still film photography. I knew that I wanted to do digital. So I think I did go online and found that people were talking about a cheaper way to get into it if you don't want to buy a telescope is just to buy a star tracker. And at the time, there was only a couple available, and it wasn't like today where we had a bunch of different choices. So the one I bought was called the Astrophotography. It looked like that. I sort of like the look of it. It sort of looks retro-futuristic or something. But it's basically like a souped-up barn door tracker. Basically, it moves your camera against the Earth's rotation for about 90 minutes, and then you have to rewind it. So it's not the most convenient tracker, but it does work really well, actually. And so this was in my backyard in April 8th, so very light polluted sky, Newark, Delaware. And on that very first night with the star tracker, I was able to take this picture. This is just a single exposure straight from camera. But I was amazed that in a single picture, a single like 1 minute picture, there's color there. That's real color of a nebula, millions, billions of years away, or miles away, and I was just like, how could that be possible? That here in my light polluted backyard, I'm taking a picture with just my normal DSLR, a crappy telephoto lens, and I'm getting the color of a nebula. And I couldn't believe that. So that was really sort of when I got even more obsessed. This was 2017. And within a week, I had downloaded PixInsight. It was getting really into all the online information available already in 2017. There was a ton of stuff out there, actually. Back then, it wasn't like YouTube, like what I'm doing now. It was really, a lot of information was on Cloudy Nights forum and things like that. But there was still a lot out there. Okay, then I've been thinking, in putting these kinds of presentations together, this is how I started in 2017. This was like probably the lowest barrier entry point to a lot of astrophotography in 2017. Nowadays, it amazes me that with our iPhone, we can get amazing single pictures of the aurora, and they look like that. like about as good as what he took in Iceland, 10, 11 years ago. This was from last year, and I saw so many pictures of people taking pictures of the aurora over the past 2 years with their cell phones. My mom, when she was out with me, because this was at our cabin in Wisconsin, and she came out and I said, well, take a picture of it with your cell phone. And she did it and could see those colors, and I was just like, this is amazing. The barrier for entry is so much lower with smart scopes too. But I think that it's just going to keep getting better in terms of how we can get people into the hobby with accessible technology. And so, one thing that I want to talk about in this sort of overview is that there's many different kinds of astrophotography or types of astrophotography, and the gear that you need to get into these different types changes, right? So if you wanted to do something like this, like narrowband nebula pictures, you can't do that with your cell phone, right? So of course there's all kinds of different gear necessities here. And there's no astrophotography gear that really excels at everything, right? Like this is a solar scope, so you could do this picture with it, but you can't really do anything else with this telescope. So there's definitely sort of specialized gear as we get into different types of astrophotography. Okay, and this is my attempt to break it into 4 types. Earlier, Bill called this Astroscape. This one goes by a bunch of different names. I'm calling it Nightscape here. It's often also called landscape astrophotography because it's when you're doing a wide shot, like I was doing with the aurora. You're trying to get a nice foreground into the picture, and then something brilliant happening in the night sky, but it's a really big scene. Like the aurora is a really big scene, the Milky Way is a really big scene. That's Nightscape. There is a newer type of astrophotography that is combining nightscape with deep sky called deepscape, where it's using like a telephoto lens, and so you're getting a little bit of the foreground and then a deep sky object above that. So there is a little bit of crossover between some of these, but nightscape generally means wide field with the landscape. This top one, solar, lunar, and planetary, you could call it SLAP. It's those are grouped together, even those are different objects, is they're all solar system objects, and you would use the same, or you can use the same kind of technique, the same kind of imaging technique with all those objects. One of the popular imaging techniques is called lucky imaging, where you use a big telescope, you're really, really zoomed in on these objects, and then you use a video camera using really, really short exposures, and you're trying to beat the wobble of the atmosphere. So you're trying to find these little moments where the atmosphere sort of is stable enough that you can get a clear picture of things. Because even though these objects are closer to us physically, in terms of their apparent size in the night sky, they're much smaller. And so they're a little bit more challenging. This is a type of astrophotography that I tried early on in like 2017 and realized it didn't excite me as much as some of the other types, so I've not really returned to it that much. Deep sky is definitely the one that I love the most. It's everything that's outside of our solar system. So nebulae, galaxies, stars, star clusters, everything like that. And then scientific imaging is something that I'm just starting to get a little bit into. I was exposed to it a lot when I worked at the Center for Astrophysics, but this is how professional astronomers use astrophotography today. Instead of just trying to take a nice picture of the sky, they'll put in a prism or they'll put in a spectrometer or some different little instrument to tell us something about the photograph that's coming back. So they'll break up the colors of a star, and that will tell us all the different gas elements that the star is composed of, and that can tell us a lot about what that star is doing, where it is in its life cycle, all that kind of stuff. But what's cool is that there's always been opportunities for amateurs to do scientific imaging. There's a group called AAVSO, the Variable Star Observers. So they look at just variable stars, stars that change in their brightness. There's a bunch of different ways to get involved with scientific imaging as well. Okay, so I'm going to now go through these types. This is just an overview. Here's some of the objects that I would call nightscape kind of objects. Ones where you're going to maybe do a wide field with landscape. We've already covered Milky Way and Aurora. Another type is star trails. So star trails, instead of a picture where you have a bunch of pinpoint stars, you do a stack of exposures, or you just let your camera take a really long exposure, and because of the Earth's rotation, the starlight is spread into an arc, or a line. And basically, by spreading out that starlight, what's really cool about it is you can see that when we look at the stars, they all just look like pinpoints of white. But of course, if you look at a star through a binocular or a telescope, you can see that the stars do have different colors. If you look at Antares, you see that that's red. If you look at Vega, it'll probably look white because it's so bright, but it is a blue star. But when you spread out the starlight, you can really see those star colors. You can see that actually the stars have all these different colors, from red to orange to white to blue, everything in there. Another thing that's very close to Milky Way is take a picture of the entire night sky. That's with a fisheye lens. Another kind of nightscape photography is whenever a comet comes along, you don't need specialized gear to take a picture of a really bright comet. If you hear the news, it's a comet that you can see with your eye, then you can also take a picture of it with just normal photography gear, and they can come out really well. The last one that you could do that with was called Atlas something, Atlas 2020. I can't remember. But then before that, there was a really nice one called Neowise, and that's what that one is there. Another thing you can do, and this is often with Milky Way, is called light painting. So basically, you don't want to do this at a star party because people will be annoyed with you, but you can take a light and try to do something interesting in the foreground. So that was just me playing around, just sort of moving the light around. But you can also do it more subtly and just sort of subtly light up a tree or something to get an interesting composition. Okay, nightscape is in one way one of the most accessible ways to get into astrophotography, because if you have any kind of camera, whether it's an iPhone or a DSLR or mirrorless camera, you probably have everything you need. You set it up on a rock or a tripod, point it at the night sky, and you can take a nightscape picture. But on the other hand, it's not as accessible as some other types because you really want a good location, a good dark sky. Here in West Virginia, it probably is easier than some other places, but if you're in like New York City, you're probably not going to get a really nice nightscape picture. It's going to be a lot harder. Just because of all the artificial light pollution, you're never going to get a really nice Milky Way picture. You'll never really get a chance to really see the aurora unless it's like a once-in-a-lifetime kind of solar storm. So this is a way that we often break up the amount of artificial light pollution. It was scale invented by John Bortle, who is an amateur astronomer. He devised the scale and published it in Sky and Telescope magazine maybe 30 years ago, but it's really taken off in the amateur astronomy community. It's called the Bortle scale, and it goes from 1 to 9, and it's a visual scale. So basically, you can read the article, and he describes how you can just do this with just your eyes. You're looking for, well, can I see a magnitude 5 star? Can I see Andromeda naked eye? How brilliant is the Milky Way overhead? And just by sort of going through this quick test, you know which Bortle number you're in. There are more objective ways to measure sky brightness. We can actually use a little meter and measure it that way, but this is a way you can just do it without any specialized equipment. And so for nightscape photography, I'd say that Bortle 4 or darker is the best. Okay, and then in terms of gear, I'm going to break these down into sort of some categories. The minimal kind of gear I would suggest is just your smartphone and probably a little smartphone tripod. You can get these for about $10 on eBay or Amazon. If you don't have one of those or you forgot it though, you really, a phone is small enough that you could just sort of prop it up on something, prop it up on a rock or something around. The nice thing though with the tripod is then you have full access to your screen, right? If you're propping it up on something, then it's harder to really see the screen and dial things in. But this is a sample photo that I took with just a smartphone. There's an app for iPhones, but there's also apps for Android that allow you to do star trails photos. And actually some of the smartphones now, they know that people are going to want to do this, and they've actually even built it into your main photo app. If you click on more, you might see a star trails photo, and you can just click on it and try this. And what this does is, a smartphone can't take just like a half an hour long photo. What it does is it takes many 5 to 10 second photos in a row, and it stacks them together in the phone. It combines all the photos together, and that allows you to see this rotation of the Earth. And this center is our North Star, which if you think of the Earth's rotation, and you just think of that we're rotating around this pole, and you can imagine an imaginary line up there, it's right there. And the reason that this is circular is because we're rotating around that pole. There's a bunch of other, I had a whole presentation on star trails because I find them interesting, but like, you can see that the lines out here are much longer than the ones up here. And if you think of like how a top works, it's like, yeah, the points closer to the center of the top aren't going to rotate as much as the points out here. And so this is like a crazy thing to think about, that it's all moving at the same rotational speed, but the stars appear to move faster out here away from the pole, and they appear to move much slower in towards the pole. And we can actually take advantage of this if you point your camera right at the North Pole, the North Celestial Pole, you can take a much longer picture because the stars don't move as fast and you can still get round stars. So there's all kinds of crazy things with star trails that are interesting to think about once you take a star trails picture. Okay, I already talked about astro time-lapse and aurora, but to give you an idea of the kind of gear you would use, you want a wide, fast lens for this. So it doesn't have to be super expensive. Rokinon makes a good one at 14 millimeters. That's what I used in Iceland, and I think it's a couple $100. One other thing to consider is, can your camera take many pictures in a row just built into it? Or do you need what's called an interval timer or intervalometer externally? And with that, so look in your menu. If you see a little option for interval timer, then you're good to go. If you don't see that though, you might need to buy a little device to take many pictures in a row. Another thing that's not pictured here on my lens, but if I actually was shooting in New Hampshire, I would always have is a lens warmer. In astronomy, we'll call this a dew heater band, but it does the same thing. It just keeps the front of your lens slightly warmer than the ambient temperature to keep moisture off of it. Because otherwise, if your lens gets colder than the ambient temperature, you'll see that it just gets a bunch of condensation. That's hard to get off. If you're at home, you can use a hair dryer, but if you're away, you might find that condensation, even if you wipe it off, it just comes right back. So it's best to prevent it in the first place and get a little band that warms up your lens. Okay, nightscape, when you're getting a little bit more experience, you can add a star tracker, just like this one here. This is the Skywatcher Star Adventure 2i. It's a really popular one, but you can also get a Move, Shoot, Move, which is even cheaper. I think Move, Shoot, Move starts at around 150 to 200. That one's more like 400. But this counteracts the Earth's rotation, allowing you to get longer exposures. So you can get, a 1 minute long exposure of the Milky Way and not have to do anything with it. It'll look really nice just in camera when you use a star. Okay, the next big type of imaging is deep sky imaging. These are some examples of deep sky objects. So we have star clusters. This one you're seeing here is one of the biggest star clusters in the sky. It's the Sagittarius star cloud. But we have all kinds of different star clusters. We have open clusters where we just sort of see a grouping of stars that look good. And then you have globular clusters where it's an actual kind of object where all the stars have been brought together like that. I don't have an example, but they're really neat to look at through the globular cluster. You have nebulae, those are obviously my favorite type. These are clouds of gas out there in space, and those are broken up further. This is a reflection nebula, meaning that we have these, a star cluster, the Pleiades star cluster, which is these bright blue stars, and then the dust around them is just the light from the stars being reflected, which makes the dust clouds blue. And then you have galaxies, of course. For people new to astronomy, or for when you show your friends, I find the galaxy photos are the ones that wow the most, because they're like, wow, you took a picture of another galaxy? That's pretty amazing. This is called Bode's galaxy, and it's Messier 81. It's a nice face-on spiral, so that means that we're sort of seeing the whole galaxy, but there's a bunch of different galaxy types as well. Okay, and the nice thing about deep sky imaging, and the whole reason that I sort of discovered it, is because you can actually do it from anywhere with the right gear. There's a lot of people who are very successful doing it from the brightest places on Earth. You can do it from a city if you have the right filters and different things and you want to try it that way. But I'll go through some different types of gear that you could use. The first type is basically just like what we have with Nightscape, except change the lens. So if you have an interchangeable lens camera, like a DSLR or mirrorless camera, just take off the wide-angle lens and put on a telephoto lens, right? So then you're going to be more zoomed in on the object. And what I found is that you don't actually need a tracker to get started. You can take many, many short exposures and stack those together and get a pretty good result. At least a good enough result to see the color of these objects and see their structure and things like that. So this sample photo that you're seeing here was just taken on a tripod with a telephoto lens and a DSLR. So I just took many, many short exposures and stacked them together. If you were using a tracker, you could take fewer, longer exposures and get a slightly better result. But when you're just starting out, maybe you don't want to buy any specialized gear. So I say this is for someone with a photographer background. If you already have the photography gear, just go out there and try it. You don't need to buy anything right away. Now, what I love about smart scopes is that they're enabling people who are interested in astronomy and astrophotography to get into this. They don't even need the photography background. You don't need to know how to operate a camera to use this. Because they've made it so simple with the app that basically they automate everything, right? You don't have to learn how to focus on the stars, you don't have to learn any of this. You just can go into the app and say, I want to go to Messier 45, you type that in, you say go, it will go to it, it will autofocus, it will do all these things right from the app. So it's a really nice way because I came to astrophotography from photography, but I meet people all the time that want to get into astrophotography and they've never taken a photo other than with their phone. And so it's like, this is a really cool way to get into it for those kinds of people. If you don't already have the DSLR, if you've never really been that into photography, but you want to get into astro, I would say get the Smart Scope. And personally, I've tried the different ones. I like the C-Star, but I've heard a lot that the Dwarf 3 is really good too. Those are the two main ones that are really, people are finding they really like a lot. There are some other options like the Vaonis, the Spera, and the Celestron something, but those are usually a little bit more expensive. Well, these ones are going for like $500 and under, so pretty affordable way to get into it too. Okay, a little bit more intermediate way when you're a photographer is just to add the star tracker. There's a lot of different star trackers out there. So earlier I mentioned this one, the Skywatcher Star Adventure, but this is a 3D printed star tracker. I see there's a 3D printer over there. So you can now 3D print all of the different components of a star tracker except for the electronics, and then just buy those and add those in. And if you do that, you can actually build a star tracker much cheaper than maybe ever before. The only thing that would be even cheaper than that is like a barn door tracker. But this is a lot more capable than a barn door. I think I found that this actually the OG star tracker can get better results than the Skywatcher for cheaper, but with a little bit more work on your end. But if you're like a real sort of nerdy person and you want to do all this 3D printing and electronics work, it's a lot of fun. He also sells it without doing all that. You can just buy it as a kit and put it together. And it's fun to support this guy that just had this idea and built something pretty cool. Okay, and then the intermediate that you don't necessarily need a photography background to do is, if you think of the C-Star, ZWO has like an advanced version of that called the ASI Air that basically has a very, very similar app, but you need to bring your own mount and telescope and the different components and put those together. But ZWO is trying to simplify that as much as possible, and they now have a camera that has an ASI Air and what's called guiding and all these things built right into the camera. So this is almost like a smart telescope just in the camera. It's a smart camera. You just attach that to the telescope. You can use any kind of mount, and this is a ZWO mount, and you have a whole kit that probably only needs 2 or 3 cables. So this is a lot easier than it used to be, where we'd have to maybe have like a dozen cables on our kit and figure out how those all work, and cables fail, there's just a lot of problems. So ZWO is doing a lot of stuff to make things really easy. I was skeptical when I heard about this, but then I actually tried it, and in one night I could get, like, just like with the C-Star, you can get 5 objects and they all turn out really great. So if you want something that's just like, you get out there in the night sky and it's fun, and you can capture pretty nice pictures just right away and get a bunch of them in one night, I think this is a really nice kit. But it does get more expensive. And the reason you would maybe go from something like the C-Star to something like this is if you weren't happy with the resolution and things like that of the C-Star. It's a smaller chip. This picture is like 5 to 7 times bigger, I think. So when you print it out, it's like these prints over here. It's more impressive when you print out something like sensory. Okay, and then going to advanced, I didn't have a picture of the Pleiades with this kit, but the reason to go to the way more advanced stuff really has to do with the kinds of objects that you can capture. So this is called the Squid Nebula. It was only discovered in 2011 by a French amateur, and it's really, really difficult because it's so dim. The reason it wasn't discovered until 2011 is because of how dim it was. So even though there have been many pictures of that part of the sky, unless you use a particular filter and really get a very, very long stacked exposure, you're never going to see that object. And so the reason to get more into advanced gear is if your interest starts going into these more obscure things in the night sky. Beyond the typical ones we shoot, like the Messier objects and things like that. If you're starting to get into, I want to discover my own nebula, that's where you can start getting into the advanced stuff. Okay, so the next type is solar, lunar, and planetary. I'm not going to spend too much time on this because this is, again, something I'm not specialized in. But here's just sort of a sampling of photos. This one was all taken by one person. So you can see all the different planets that you can capture, all the different solar system planets and objects that be captured this way, including satellites. So this is a picture of the International Space Station from an amateur. Okay, and then just like deep sky, you can do this from anywhere. You can actually do this kind of photography from anywhere without even specialized filters. But what it does get specialized is the telescope. You can't really do this well with a small telescope. You really want bigger telescopes to capture these objects. So the only telescope that I have that's really appropriate for it is a Dob, but I'll talk about this more in the next presentation. Using a Dob for photography is really difficult, especially if you don't have tracking, because you're really zoomed in on the night sky, and you don't have tracking, so you're just trying to find things and keep them on the camera. It's really hard, but you can get results good enough where you can see Jupiter's bands and the rings of Saturn and things like that with a Dob. And another way to do it that's even easier than attaching your DSLR like that, which people do at star parties all the time, is you're just looking at the object, the eyepiece, just put your smartphone right on the eyepiece and take a picture that way. It's called afocal photography, and you can get results basically as good as that that way. But the people who really get into solar, lunar, and planetary photography often still use the Dob, but the only thing that's different is that the Dob is motorized. So, right, so that there's a tracker, a motor and tracker down here, and so it's tracking the night sky, and that makes it so much easier. You can also use other kinds of telescopes, Cassegrains, whatever, but the nice thing with Dobbs is that the thing that's really important is aperture for this kind of photography, how big the telescope is. So you can get really big Dobbs and do really nice work with this kind of stuff. Okay, and then the last type, this is something that I'm just getting into. I did take this picture of some stellar spectra because I have a little diffraction grading. But this is breaking, spectra is breaking up the stars' colors into their rainbow, and you can see the absorption lines and do all this kind of different stuff. Another really cool thing you can do is exoplanet transits, and this is all related, exoplanets and variables, where you're just looking at the brightness of a star. And then you can take many exposures over time and plot those out and see, oh, the star is getting dimmer right here, and then it's getting brighter again. What's happening? It could be that it's a variable star, so some stars just change in brightness over time due to the nature of the star itself. Other stars, things are passing in front of them. And so this is how we can detect planets on other stars, and you can do exoplanet research with the C-Star S50. I have a friend who does it, and you're probably not going to find a new exoplanet, but you can look at ones where we know they are on the stars and actually see there actually is an exoplanet there, and then plot that out with something as simple as a C-Star. And then stellar spectra can be very easy too. I'll probably have a video coming up on this at some point, and you can just put a little diffraction grating in front of a telephoto lens and get stellar spectra. All right, I'm going to stop here and see if there's any questions about the overview. Thanks so much.
So, I know we were jumping about we built a lot of beginning and what's the biggest or the most common thing that they say or a challenge for as masters for beginning and
Yeah, the question was, what's the biggest thing that beginners have challenge with? And not excluding smart scopes, as those do the focus themselves, I'd say it's focus. I find that a lot of times people will show me, and they might not know it's focus. A lot of times people will show me a picture, and they say, I know something is wrong with it, but I don't know what it is. And I zoom all the way in on the stars, and the stars aren't perfectly focused. And if the stars aren't perfectly focused, you're never going to get the detail you want on the deep sky object. I could probably find a slide in one of my other presentations, but a good tell for focus is if you really, really zoom in all the way on your camera and you don't see lots of little stars, you're not in focus. Because you'll start seeing stars when you're close to focus, but only the bright stars. When you really snap into focus, that's when you see all of these little tiny stars littering your field. And if you're new to this, they might even look like noise because they're so small. But that's really the tell. The other way I tell people to look for this is they're often showing me a picture, is if you really look at a bright star, the center of it should be the brightest part, right? But a lot of times when you're slightly out of focus, you'll start seeing a donut where there's a ring of light and then the center is actually slightly dimmer. And I think the reason this is so hard is, especially with DSLR photography, is we're looking at a bright screen at night, and so it's like our eyes get adapted to this, and then we look at this bright screen and it's sort of a shock to our eyes, and it's hard to even see, even all the way zoomed in, that you're really in focus. And then I often recommend what's called a Bottomov mask, but depending on the lens, those sometimes are hard to use too. So I think focus is just like sort of an issue that can plague people, especially beginners. What else? I'd say the other one is just conditions. Like, you know, there's so many things that can go wrong with conditions, whether it's light pollution or haze in the sky and things like that. It's actually rarer than we think of just getting the perfect night for astrophotography. And when you're looking at your data, if you're a beginner, it can be hard to sort of understand, well, what is me and what is the conditions of the sky and things like that. Yeah.
Can you talk a little bit about that?
Oh, sure, yeah. So the question was about back focus. And so one thing is just focusing a telescope, right? And we think, okay, if I've reached focus, I've reached focus. But with a telescope system like this, there's another concept called back focus, where there's an optimal distance from the focuser threads to the camera's sensor. It's called back focus or back spacing. And if you use just a telescope meant for visual, there probably isn't an actual strict back focus requirement. You just attach your camera. But for any kind of imaging telescope, we usually have what's called a corrector in here, a field flattener or a coma corrector or a flattener reducer, and those do have strict back focus. And so all that means is that you read what the specification is, like it will say, this has 55 millimeter back focus, and then you have to make sure that the number of spacers and things in here, from the camera sensor to the threads of that field corrector, is exactly that specification. The reason it's usually 55 millimeters is because the first kind of photography that was done with telescopes was DSLR. And with a DSLR, they designed there's 44 millimeters of space between the sensor and what's called the flange of the DSLR. And then they found that the thinnest they could design was called a T adapter to attach it to this telescope and make it stable was 11 millimeters. So that's why we got 55. It's 44 plus 11. And then that standard just sort of stuck. Even though that we're now, many of us are not using DSLRs anymore, but these Astro cameras, a lot of people ask, well, why don't they make it more generous now so we can fit in more stuff here? But the answer is because they've already designed this standard. It would be a lot of work to say, well, now we're going to have telescopes that have 100 millimeter back focus, and for you DSLR users, you're going to have to just buy a bunch of spacers and all this stuff, because they've already designed it to be simple. And so it's still an open question, but like that's why, is that they've already designed all of the stuff around 55 millimeters, so that's why you'll see that over and over again. It becomes an issue when you want to include more things between your camera and your telescope. So you can see this one here has a filter drawer, but let's say you wanted a filter drawer and an off-axis guider and a camera rotator. Once you start adding all these accessories in, you just quickly run out of space. And so then you have to make the hard decision of like, well, what's important to me to actually put in?
Okay, yeah. Since you just pulled out that filter, I read or saw a video online that you had a filter in between the telescope and the camera, that you have to take. Get it very precise. They said you take the thickness of the filter and divide by 3, which my filter is around 1.8 to 8.6 millimeters, and you add 26 millimeters of shim in there, you actually divide.
Yeah, so the question is about if you add a filter between your camera and the telescope, do you have to add a little bit more spacing to actually get the correct back focus? And yeah, the technical answer is yes. And I run into this when I'm using very thick filters. So there's a filter company that doesn't exist anymore called Astrophotography that had 3 millimeter thick filters. So that's quite thick. And so that would actually change the back focus by a whole millimeter. And the tolerance for back focus is often plus minus 1 millimeter. So you're right on the edge of that. And so in that case, yes, I did have to actually add a spacer. I found that usually with what you're talking about, the 1.8 millimeter thick filter, so that would throw off the back focus by 0.6, you're probably within the tolerance of that field corrector and don't have to do anything. But the way you can tell if you have to do anything is just looking at your corner stars. So if you look at the stars in the corner of an image, if they're slightly going in towards the center of the field, or they're slightly like this, sort of parallel to the center of the field, then your back spacing is probably off. If they're all equally going in like that.
If you wanted to try, where would you put the shim?
Oh, Oh, sure. You would just put it, and the way I would do it is, go to Gina Astro, website, and they have little shims that are metal, so they don't flex or anything. And they're already diameter for this stuff. And then you just put it right over one of the spacers. So you still will have enough threads, and you just put it between the spacers. And I think that's the best way to do it. Unless you're going, like, and they make those in, no, that's the way I do it, because they make them in all sizes. You can do 0.1 all the way up to 1. Yeah, if it's not, that's the thing I often tell people. If something is already working, don't try to fix something that's working. If you're not seeing something wrong with your telescope, a lot of times we obsess over these things, and it happens with guiding all the time. People tell me, well, my guiding number isn't this, and I'm like, well, are you getting nice pictures with round stars? Yes, well then don't worry about getting your guiding even better. But you know, a lot of times if you have like the engineer kind of mind, you're like, but I know I can make it better, and so then you'll just keep going and going and try to make things better and better. But yeah, you'll definitely get into these kinds of diminishing returns where you probably are not seeing any difference between 0.7 arc second guiding and 0.4 or something like that, or changing the spacing by 0.3 millimeters. Maybe you can see it numerically, right? So if you change the 0.3, you might be able to use a tool that tells you that your back spacing has gotten better, but you might not be able to see it visually.
I'm brand new with this stuff. I was a visual observer for a long time. You mentioned one place in there that there was the ASI system that has the camera, guided electronics,
Yep.
all that kind of stuff in that one piece.
Yes.
For a beginner, is that a good place to start?
Yes. And they now make it with different size chips, so at different price levels. So they make one called 585 Air, which is a smaller chip, and they make one called the 2600 Air, which is a bigger chip. I can't remember the exact prices, but they're somewhere between like $1,000 and $2,000, and I think they're an excellent place to start because it just adds so much in there. Now, there's the one caveat to that is you do need to think about, and I'll talk about this in my next presentation, what telescope you're pairing it with. Because when the guide chip is in the camera, you need that guide chip illuminated. And so if you are wanting to put that onto, let's say, a Schmidt-Cassegrain with a reducer, the illuminated circle might only be 30 millimeters, and that's not going to be enough to really illuminate that guide chip well enough to get good guide stars. So it does require basically that your telescope, just have a nice big image circle so that you can really fully illuminate. But other than that, I just found they work really, really great.
You also have two versions of these. You have the one-shot color and
Oh yeah, Bill brought up, yeah. So with each of those Air models where they build in the guider and the electronics and everything into the camera, you have a color version and a mono version. So you can go right into mono imaging with filters as well with those now, which is pretty neat. The one, that's a good point. That another thing I'd say about another sort of caveat is with filters. If you're using very, very small bandpass narrowband filters, again, you might not have enough light to get good guiding. So there's a few little caveats, but for beginners, I don't think you're gonna want to go right off into like 3 nanometer narrowband unless you're imaging from like a really light lit sky. All right, well, I have another presentation after the break all about telescopes, so we'll stop here.
good. Yep. So we'll give Nico about 10 minutes or so. So let's just say we'll be back at 22. That's a little bit longer than 10 minutes. So 22.